A very good evening to one and all, and I welcome all of you for this special public lecture, which we are organizing jointly with the National Academy of Sciences, India Delhi chapter, and the Dayal Upadhyaya College University of Delhi under the aegis of the DBT Star College program. Today we have with us Professor James Durrant from Department of Chemistry, Center for Processable Electronics, Imperial College London, and is also associated with specific IKC, College of Engineering, University of Swansea, United Kingdom. And he'll be talking to us on the topic charge carrier dynamics in organic and perovskite solar cells. So before inviting Professor James to deliver his talk, I will briefly introduce him to all the attendees. He's a professor of photochemistry in the Department of Chemistry, Imperial College London. He's also a professor in College of Engineering, University of Swansea. His research interest in the area of photochemistry of new materials for solar energy conversion, targeting both solar cells, photovoltaics, and solar to fuel, that is artificial photosynthesis. His group is currently addressing the development and functional characterization of organic and perovskite solar cells, as well as photocatalysts and photoelectrodes for solar fuel generation with funding from the EPSRC, WAG, EC, ESF, and the industry. More widely, he founded the UK Solar Fuels Network and leads Imperial Center for Processable Electronics. He has published over 550 research papers and 5 patents, which have been cited over 50,000 times. He was elected a Fellow of the Royal Society in the year 2017. With these words, I now invite Professor James to kindly share his screen and deliver his talk.
Oh, that's it. Can you see that okay?
Absolutely.
And can you see my cursor?
Yes.
Perfect. Very good. Thank you very much, Professor Saxena, for kind introduction and indeed for inviting me. It's a great pleasure to talk to the National Academy of Sciences India. I've had many collaborations with colleagues in India over going back well over 10 years, with originally the APEX project and now our project Sunrise, which have been focused particularly on the area of organic and perovskite solar cells. And so I've had a great pleasure to work with many colleagues across India in this field. And so for that reason, I was particularly pleased to be able to accept your invitation. I'm going to focus primarily on the dynamics of charges in 2 examples of relatively new photovoltaic technologies. Organic solar cells based upon blends of an organic donor and acceptor sandwiched between electrodes, and these new hybrid organic inorganic materials, these organo-led halide perovskites, which is really the new wonder material for generating high performance solution processable solar cells. What I thought I'd do is, first of all, discuss some of the challenges and opportunities for these organic and perovskite solar cells. I'll then talk about kinetics. As you would have seen from my introduction, I'm primarily a photochemist, and I like using laser spectroscopy to measure carrier lifetimes. And so I'll be talking about the connection between kinetics and energetics and efficiency, what we call the kinetic challenge or the energetic cost of lifetime gain. I'll then go on to talk in a little more detail about the similarities and differences in the carrier dynamics between organic and maybe the perovskite solar cell, which is has the closest parallel to organic solar cells, so planar perovskite solar cells, typically with organic interlayers. And then at the end, I'll just briefly touch on a growing area, I think, which is taking the materials which we've been working on for the organic, and indeed sometimes for some groups, the perovskite solar cells, but applying them not to generate electricity, but to make green hydrogen from sunlight. And I'll just touch upon some of the excitement and challenges there. if I start thinking about solar and why we want new solar cells, then it's important to recognize that silicon PV is a success story. There's now been over 600 gigawatts peak of PV installed globally. And indeed, India now is increasingly installing significant amounts of PV, as you can see from this plot on the right. It's a major industry. It's $500 billion a year, and it's growing around 20% an annum. Even in the UK, which is not the sunniest part of the world, we have 13 gigawatts peak, and it produces around about 3% of our electricity. And you can see an illustration of the growth of PV. This is my son outside his primary school in 2000, when they installed solar-powered parking meters outside his school. At the time, that was the first example I saw of PV installed in the UK, and I was very excited. Of course, 15 years later, we no longer have solar-powered parking meters, we have solar farms generating significant amounts of power. And that's as a visual illustration of a change of scale we've seen over recent years. Of course, this growth has been driven primarily by cost reductions. It's driven partly by policy and concern about environmental impact of fossil fuels. But the particular growth of solar has been driven because the cost of solar cells has come down dramatically, and particularly the cost of silicon solar cells. We're now at the stage where if you put up a photovoltaic system, then the cost of the solar modules is only a third of the cost of a system. And in many parts of the world now, if you want to generate electricity, then solar photovoltaics is cheaper than either coal or gas. And so in that sense, solar is already a success story. And you could argue silicon's already doing a fantastic job. Why do we need anything else? Oh, what's happened there? Goodness, I don't know what happened then. I'll try that. That's better. So we need to think about why or what are the challenges going forwards. Of course, one challenge is to make those silicon solar cells more efficient. And this is the strategy which, for example, Henry Snaith and Oxford Photovoltaics are driving, which is the idea of making silicon perovskite tandem solar cells. This is certainly a very exciting area of research and moving towards large-scale commercial manufacture. But it's not an area where I'm particularly an expertise, so I'm not going to touch so much on that in this talk. Another strategy is to think about the 2/3 of the cost of those PV systems, which is not the solar cell, and thinking about how if we design solar cells in different ways or different materials, we can reduce what is called the balance of systems or the installation costs of those solar cells. And we can also think about how we can integrate solar cells into products which increases the range of potential markets. So you can see, for example, here the idea of having semi-transparent windows, where the window is the solar cell. And this idea of integrating solar cells into buildings is something which my colleagues in the specific centre in Swansea are doing a great deal of work on. These are two illustrations of their active classroom and their active office, which are off-grid energy positive buildings in a part of the UK which is actually rather unsunny. Swansea is not despite the blue sky you can see here, that is a rather unusual day in Swansea. What was interesting there was that in order to build these off-grid buildings, they looked at different PV technologies to put on the roof, and it turned out that the cheapest building did not employ silicon. It employed flexible CIGS, copper indium gallium diselenide solar cells, laminated onto the steel roofing. The reason was that silicon is heavy. It's encapsulated between two glass plates. And to put silicon PV on the roof, you'd have had to build a much stronger structure of building. These CIGS solar cells are more expensive and less efficient than silicon, but the cost of a building powered by CIGS was cheaper than the cost powered by silicon. And that was a very interesting realization. And you can equally see the advantage, for example, that you can imagine structures such as this one here, where the PV roof is curved, which has interesting opportunities for aesthetics. I'm very pleased to hear that my colleagues are now moving this idea of active buildings, of solar-powered buildings beyond the UK. And this is an example of a solar-powered active community building, which is going to be going up in Kuded in India over the next 2 months as part of UK-India Project Sunrise in partnership with Tata. But that's all with a standard, these SIG solar cells. They work well because it's a thin film technology, which means that it can be deposited on a flexible substrate, but it's not the ideal technology. It's not as efficient as silicon, and it's a lot more expensive than silicon, at least particularly in this flexible form. What I'm particularly interested in is, before going on to that, the third area, which I'm going to come to towards the end of my talk, is the issue that as we have our growth in photovoltaics, then we increasingly need to think about strategies for storing energy. We have increasing the challenge, certainly in the UK, and I imagine you will have the same in India soon, where the intermittency of solar power puts particular strain on our overall electrical power generation and requires us to think about either battery technologies or increasingly technologies associated with photovoltaics plus electrolysis to make hydrogen, to make green hydrogen, or indeed direct pathways to directly synthesize green hydrogen from water using sunlight. I'll come back to those pathways at the end of my talk. In terms of the materials which excite me, then I'm particularly interested in the idea that we can print solar cells. And so the idea here is that we start off with semiconducting materials which are soluble and can be deposited by a printing technology as an ink onto a substrate. The first example of this really were dye-sensitized solar cells, but more recently the organic and maybe most recently the perovskite solar cells have attracted extensive attention. By being able to print a semiconductor onto a flexible substrate over large areas, this allows you to think about, for example, printing solar cells roll to roll onto flexible sheeting. It allows you to think about making solar cells which are lightweight, which in principle are low cost if they can be efficient enough, which can be colored because many of these materials have tunable band gaps. We can coat conformally onto a surface if we wish. And indeed, as we saw an example from Helitech a minute ago, we can have devices which are translucent, which absorb sunlight in some regions of a spectrum, but not in others. These all allow us to think about applications which are different to the existing technology. In terms of efficiency, then the perovskite solar cells have already advanced its efficiency substantially, but the organics are starting to catch up. And this catch-up in efficiency has been driven by a transition from devices based upon a semiconducting polymer blended with a fullerene acceptor, which was essentially the state-of-the-art for organic solar cells from the late 1990s up to around about 2015. And the exchange of these fullerenes with alternative, what are rather not very creatively named, but at least it's clear, non-fullerene acceptors. And this transition from fullerene to non-fullerene acceptors has driven a substantial increase in device efficiency, and very often coupled with greater tunability, greater stability, and potentially lower cost. As an example of the efficiency enhancements, and this is just some data we collected actually in collaboration with JNCSR in Bangalore, showing that when we went over from a fullerene to a non-fullerene acceptor, we were able to have tunable light absorption across the visible spectrum. And both of those light absorbers were able to separate charge from their excited states. And so we had electron transfer from the donor or hole transfer from the acceptor, driving current generation in those devices. The motivation behind these printed solar cells is the idea that we can go after targets, after applications which silicon are not so good at. And so the particular attributes we're talking about is that they are flexible, they can be lightweight, and they can be translucent. And this enables us to think about how we can integrate them. into roofing, into buildings. We're starting to look at the potential for using some of these flexible solar cells to power unmanned airborne vehicles, for helping some of the satellite requirements or the communication requirements for Gen 5. We can imagine integrating these flexible solar cells with batteries. And indeed, we can imagine some of these translucent devices being useful in agrivoltaics and greenhouses. As one example of how these printed technologies can be integrated into buildings, the idea of using organic and perovskite solar cells for indoor light harvesting is attracting increasing attention. There's a large growth in what is often called of sensors and devices for the Internet of Things in our homes. This Internet of Things needs powering. Currently, a lot of that power has come from batteries. But if you can harvest power from the light inside a building, then it allows you to have batteryless sensors and detectors and switches. And it turns out that both organic and perovskite solar cells can actually outperform silicon under indoor lighting conditions. You can tune the light absorption spectrum of the organic semiconductor to indoor lighting rather than sunlight. And very often for both perovskite and organic solar cells, the performance goes up as you lower, the efficiency goes up as you lower the light intensity, as you slow down bimolecular recombination losses, in a way which doesn't happen with silicon. In terms of thinking about how these devices work, and so I've talked a bit about the applications and the excitement and the idea that organic solar cell performance is going up particularly fast at present. What I want to switch gears now and talk about how these solar cells work, and particularly about some of the kinetic challenges in these solar cells. So when we think, first of all, about a perovskite solar cell, so the idea is that it's this organo-lead halide semiconductor, which is sandwiched between two electrodes. You shine light on it. It's a crystalline semiconductor with a low dielectric constant, which means when you photoexcite it, you make free electrons and free holes. One of the particular characteristics of these organo-halide perovskites is that they have mobile ions. And this means that even if the anode and cathode have different work functions, this difference in work function does not generate a field in the device, in the bulk of the device, because the ions move to screen those fields. And so charge collection of these devices is driven by the diffusion of electrons in one direction and holes in the other direction to drive current generation and performance. Organic solar cells have a similar structure, except the light absorber is now typically a donor-acceptor bulk heterojunction. So it contains both a donating light-absorbing organic material and an accepting one. The main difference is that the organic materials have a low dielectric constant, which means that photoexcitation doesn't generate free charges, it generates bound electron hole pairs. And in order to separate these excitons, these bound electron hole pairs, the exciton moves to an interface between the donor and the acceptor, and an energy offset between the donor and the acceptor drives the charge separation to enable the generation of electrons and holes, which then can be driven by the bulk electric fields from a difference in electrode work function to either contact. And so the main distinction between these two devices is the idea that you directly generate charges in the perovskite cell, whilst in the organic cell, you have to separate the charges at a junction. And in order to make sure that the excitons find an interface, typically these organic solar cells are structured as bulk heterojunctions. So an intermix, a significant intermixing of a donor acceptor material. Now, in terms of kinetics, it can get complicated. And this is just one illustration from a perspective we recently wrote of some of the processes which go on to try to, which in terms of the desired processes of exciton separation and charge extraction, in the organic solar cells and the charge transport and extraction in the perovskite solar cell, and how these processes can be impacted by processes such as polo formation, charge trapping, and particularly different recombination pathways which limit device performance. I'm not going to go into too much detail in all of this. I'm going to start off by giving a more overview picture of why kinetics are important. And for me, my understanding of why kinetics were important came from my understanding as a PhD student, where I was studying plant photosynthesis. And what is striking about plant photosynthesis, it's achieving the same general ambition of harnessing sunlight to generate useful energy. But in plants, of course, it's not making electricity, it's making chemicals from sunlight. And particularly in this case, this photosystem 2 reaction center is oxidizing water to molecular oxygen and taking the electrons, which then go on to reduce carbon dioxide to sugar. But the plants have this challenge that the excitons, the excited states, the chlorophyll excited states in a plant typically live for nanoseconds, whilst the functional timescale required for the charges to do something useful, i.e. catalysis in this case, is milliseconds to seconds. In order to gain the lifetime to drive the catalysis, the plants separate the charges. They have a redox relay which separates charges in a series of steps, rather like those donor acceptors in the organic solar cells, and that gains lifetime. And that gain of lifetime enables the photons to drive the catalysis. But that gaining of lifetime costs energy. So the plants use around half the energy absorbed from the sun to gain the lifetime to drive the function. In a solar cell, we don't need to drive catalysis. We need to enable our photogenerated charges to get to the contacts for transport. So we need to have a lifetime of our charges long enough that the charge can be extracted to the external circuit. That timescale is faster for catalysis, but still very often it's a timescale, there's a lifetime challenge, which is important in understanding function. We recently did a meta-analysis of the lifetime gain required and the energy loss associated with a device for a very broad range of photovoltaic and photosynthetic systems. This was an analysis done by Robert Godin, who was in my group and has now moved to the University of British Columbia. And this plot, so this is a plot of the lifetime gain, which it corresponds to the lifetime of the bulk photoexcitations in the material, versus the lifetime, the functional lifetime, which is either catalysis or transport, versus the energy loss, which is the difference between the optical band gap and the energy of what's coming out, which for a solar cell will be an open circuit voltage. And what you can see is that there's quite a nice correlation over many orders of magnitude and over many different classes of material between how much lifetime gain is required and what the energy penalty is, which of course loses the efficiency. The energy penalty is greater for photosynthetic systems than for photovoltaic systems because catalysis is slower than transport. But you can see, for example, here, here's our perovskite solar cells with a very small lifetime gain and a rather small energy loss. Here's the organic solar cells, rather more intermediate, a moderate lifetime gain and a more significant energy loss. This idea of that you need to gain lifetime, and that gain of lifetime has an impact on function, but you need to gain lifetime to achieve function, it's not new. And so there's a couple of examples here. This is a plot for a range of inorganic solar cells correlating with the diffusion lifetime product with device efficiency. The tau is the lifetime of the carriers in the material. D is a measure of transport. And essentially there's a correlation that if the lifetime is long or the diffusion is fast, then you achieve higher efficiency. So this is the same concept, that there is a, for these devices down here, then either the lifetime was too short or the transport was too slow and the efficiency becomes lower. And indeed, we generally see that materials with a large lifetime challenge have much difficulty achieving performance close to the Shockley Quasar limit. Of course, one of the exciting things here is how these organic solar cells are getting better, and I'll be talking about that in just a minute. Looking a little more directly, so these perovskite solar cells, they have a very low lifetime gain challenge. And you can understand this because if you measure the carrier lifetimes in a perovskite, you can measure that by luminescence, the luminescence resulting from a charge recombination of electrons and holes in this perovskite material. And you can compare that luminescence to the luminescence decays when you've added the transport layers which collect the charge. And what you can see is that the carriers in the bulk MAPI live rather a long time, while the charge extraction is occurring on timescales here of maybe 50 nanoseconds. This means that there is very little lifetime gain required in a perovskite solar cells. It's not quite as simple as this because I haven't talked here about the light intensity dependence of a carrier lifetimes. I'll come back to that in a minute. But in essence, this is why perovskite solar cells can be one of the reasons why they can be so remarkably efficient. When we compare that to organic solar cells, then they have a much greater lifetime challenge. This is the decay dynamics of an exciton in a typical donor material in an organic solar cell. It has a lifetime maybe of 100 picoseconds. This is a measurement of mobility in a typical organic solar cell, which if you translate that into transport time, gives you a transport time of the order of 100 nanoseconds. So organic solar cells have a lifetime gain challenge of around about 1,000. And of course, this lifetime gain challenge is one of the reasons why organic solar cells have a lower efficiency so far than perovskite solar cells. Though, as you'll see in a second, we're starting to make progress in reducing this lifetime gain. In particular, Christoph Babek and colleagues has recently pointed out the idea that many of the new non-fullerene acceptors, which are driving the efficiency advances in organic solar cells, have a particular advantage that they have rather long exciton lifetimes, longer than many of the other low band gap materials which have been used in organic solar cells before. And this increase of exciton lifetime is reducing the lifetime challenge required in these solar cells, and is one of the reasons for their advances in performance. One of the particular challenges in these organic solar cells is separating the charge, is separating the exciton into charges. And as we saw in photosynthesis, the gain of lifetime associated with, in this case, an electron transfer or a hole transfer reaction doesn't come for free. You need an energetic offset to drive charge separation. And indeed, we often see a correlation that the efficiency of separating the charge, measured as the quantum efficiency of a device, often shows some correlation with the magnitude of the energy offset. So in general, a larger energy offset helps you separate the charge. It's not the only determinant. There are many other determinants of the ability to separate charge, but certainly the energy offset is one of them. What's maybe more interesting is the idea that the magnitude of the energy offset required to achieve the same quantum efficiency depends upon your choice of materials. So these are data for different classes of organic materials, different series, in this case, different donors. And what you can see is that as you change the choice of organic donor, then the energy offset requirement becomes smaller. Each of these points corresponds to a different blend of a different acceptor. And indeed, the highest the latest class of organic donor acceptor materials based upon PM6Y6 in its analogues is able to achieve a high quantum efficiency with a surprisingly low energy offset. And that's, of course, one of the key reasons why these solar cells are getting more efficient. How do they do that? Well, we have this challenge that you can form bound charge transfer states at the interface of a donor acceptor because the Coulomb attraction is low. The dielectric constant is low, which means the charges are coulombically bound. And it's very easy to form bound charge pairs at these interfaces. We proposed some years ago that electrons can do the long jump. It's the idea that if you have a sufficient energy offset, then the electron can go into the acceptor and move away from the interface and relax as it does so, but only relax when it's far enough away from the interface that it no longer feels that Coulomb attraction. It then gets stabilizes by processes such as charge trapping and polaron formation. This idea that the carriers may be able to separate into free charges without having to go some thermally activated barrier from a charge transfer state has been recently supported by temperature-dependent measurements. This is some work from Ifan Dong in my group showing that essentially the activation energy for charge separation in these PM6 Y6 blends is almost zero. This was also observed by Deen recently in a paper in Advanced Materials. And so this is all quite exciting because it suggests that organic solar cells are able to separate charge with a rather modest energy loss. And that's one of the reasons why their performance is going up. Maybe more wackily, and I'm not quite sure how useful this is going to be, but we're increasingly finding that you actually don't need a bulk heterojunction to separate charge in organic films. This is an example of work we did with the University of Dresden recently, looking at charge generation in alpha-6T films. And in this case, we found that alpha-6T as a evaporated small molecule film was able to generate charge with no contact layers and no acceptor. We were able to understand why it does this from energetic and DFT calculations, which showed that this alpha-6T can form different crystal packing and different orientations as it goes down, and those either standing or lying alpha-6T domains have different energetics. And it's the energetic offsets caused by those different energetics which can drive charge generation in these materials. And indeed now there's increasing interest in trying to find materials which are able to separate charge without a donor-acceptor molecular junction. I want to talk a little bit more now about the voltage in these solar cells. So the idea is that we generate a voltage in both the organic and the perovskite solar cells because light splits the quasi-Fermi levels. So in a solar cell, it's the idea that you photoexcite it, you generate holes and electrons. In the dark, the Fermi levels in the middle and the electron and the hole Fermi levels are the same. But in the light, we generate populations of holes and electrons, which move the Fermi levels in opposite directions. And it's this splitting of the Fermi levels which corresponds to the free energy stored in those charges and corresponds to the open circuit voltage, which comes out as, from the solar cell. And indeed, what we observe is if you store more charge in the solar cell by shining more light on it, then the Fermi levels split more because the Fermi levels now start to approach the band edges and the voltage goes up. And so in that sense, as you increase the light on your solar cell, the free energy which each electron hole pair extra one you generate increases because the quasi-Fermi level splitting or the device open circuit voltage has increased. In order to understand how that connects to the idea of storing more free energy, but what's the penalty, it's important to realize that as we shine more light on a solar cell and increase more voltage, then the carrier lifetime for both these organic and perovskite solar cells goes down. So these are measurements of the range of different organic and perovskite solar cells of the carrier lifetime in the material as a function of light intensity. And in all cases, what we observe as we increase light intensity, the voltage goes up and the lifetime goes down. And of course, the lifetime is going down because as we store more and more charge in the device, then the likelihood that electrons and holes are going to bump into each other and recombine goes up, which means the kinetics of bimolecular recombination accelerate. And so we have this direct trade-off that the more you try and store energy in these electrons and holes after photoexcitation, the harder it is to extract them because their lifetime is shorter. This is another viewpoint of the idea that there's a direct correlation between the energy you can extract and the lifetime of the carriers, in this case, induced simply by changing a light intensity. Of course, how much the lifetime changes for a given increase in voltage depends upon the material. You can see that in some cases, the gradient is much steeper than in others. How we can understand that is mainly associated with how ideal the band edges are in these materials. I didn't talk about it, I'd go back a couple of slides, but then when we store charge in these materials, much of that charge is not stored by carriers at the band edges, but by charges in tail states. And these tail states can extend into the band gap, and how far they extend into the band gap tells you how much charge you store in those tail states at the Fermi level split. And of course, if you store more charge, then that tends to accelerate more recombination. And so that's not a good thing. In addition, of course, the relaxation of carriers into those tail states corresponds to a loss of energy. And what we're starting to understand is how we can design materials with fewer tail states. And in particular, we've observed recently that in some of the highest performing organic solar cells, they exhibit the dependence of charge density upon quasi-Fermi level splitting, which is almost ideal. So this dashed line here would correspond to an ideal semiconductor, which has no tail states. And so the quasi-Fermi levels, as the quasi-Fermi levels split, it's only the charge in the bands which go up. But most materials start to store far more charge because of all that charge stored in the tail states. Silicon behaves almost ideally, and we've now found examples of organic solar cells, which also behave ideally. We're fully expecting the highest performance perovskite solar cells ought to behave ideally. We haven't yet worked out the ideal data to demonstrate that. But I think that's quite important, that we are starting to understand how these solution processed materials can have, in some cases, almost ideal band energies. Understanding how this bimolecular recombination limits performance allows us to have a very simple model of how both organic and perovskite solar cells have their VOC determined. It's the idea that at open circuit, there is no current flow because you're at open circuit. And this means that the generation current, which most simply we can equate to the short circuit current with maximum charge we can get out of a solar cell, at open circuit, generation must equal recombination because the carriers don't go anywhere. And the recombination, we can simply flux, we can simply define by a carrier density and a lifetime of those carriers. And so if we can measure the carrier density and we can measure the lifetime, we can calculate a recombination flux, and VOC will be when that recombination flux matches the generation flux. This allows us, from kinetic measurements, using this very simple model, to calculate VOC simply from measurements of carrier lifetimes and charge densities. And when we calculate that VOC, we get an agreement with a measured open circuit voltage, which is typically within less than 10 millivolts for a very wide range of both organic and perovskite solar cells. That shows that this simple model works rather well. It also has the idea that if we want to increase open circuit voltage, we want to store more energy in these devices after solar irradiation, we need to increase carrier lifetimes. And from the gradients of carrier lifetime versus charge density, we can estimate and show that if we want to, if we manage to increase the carrier lifetime by a factor of 10, then that gains voltage by between 50 and 100 millivolts. When we come to comparing these dynamics between the organics and the perovskites, then, and particularly when we look at the difference between the charge transport dynamics and the charge recombination dynamics, there's a striking difference. So perovskites, the perovskite materials, have far higher mobilities than the organics. It's a more crystalline material, there's less severe charge trapping and polymeric formation, and the carriers move much faster. But the recombination kinetics are not so much faster. In other words, the carriers are moving around very fast inside the photoactive layer of a perovskite solar cell, but they are not bumping into each other and recombining faster than the organics, even though the organics are moving much more slowly. I think the key to understanding that is the idea that the higher dielectric constant of the perovskites means that the Coulomb capture radius is far smaller for a perovskite than an organic, which means that even though all those charges are moving around much faster in the perovskites, they very rarely get close enough to actually go into their Coulomb capture radius and recombine. And of course, this is quite striking because the organic solar cells have these bulk heterojunctions designed to separate the charge. And yet, even with those bulk heterojunctions, they still have far more recombination for a given mobility and carrier density than a perovskite solar cell does. And that, of course, is one of the other reasons why perovskite solar cells can work so well. It's because the carriers, when they are generated, don't see each other, and so it's much easier to extract them from the device rather than have them recombine. The last point I wanted to make about comparing organic and perovskite solar cells is the importance of contact layers and whether they need to be selective. In organic solar cells, we have these fields between the different work functions of the cathode and anode, and these fields will drive the charges towards their respective contacts. And because of that, the selectivity of those contacts is not completely critical to device performance. It helps, but it's not essential. But in perovskite solar cells, the ions in these materials, the mobile ions, move to screen a field, just as if you try to apply a voltage to water or to a salt solution, then the salt ions would move in the solution to screen the fields in the bulk electrolyte. And this means that charge transport in a perovskite solar cell is diffusive rather than drift, and it means that carriers can diffuse towards the wrong contact. And this greatly increases the requirement for having selective contacts. You can see an example here where we were looking at different organic whole transport layers in a perovskite solar cell, and these layers varied in their doping, the extent to which they included positive charges. And of course, these positive charges, these dopants, can act as recombination sites can recombine with electrons. In an organic solar cell, that doesn't happen so much because the fields drive the electrons to one way. But in a perovskite solar cell, those fields are largely screened by the ions, and now we have far more issues with interfacial recombination. And I'm not going to go into the details. There are many, many papers on interfacial recombination in the perovskite solar cells. But the key point is that it's more important for the organics, and achieving good contact selectivity is really key to achieving high performance in the perovskite solar cells, but much less critical for the organic solar cells. I'm just going to finish with a new area of research, which I find quite exciting, which is around the challenge that as we start to understand how to make cheap and efficient solar cells, then we increasingly need to think about how to store that energy. And we also need to think about how we decarbonize transport and decarbonize our chemical industry and our fertilizers. And for all of those, we need the sustainable synthesis of chemicals and fuels, and most simply hydrogen. And for materials which I've been talking about today, these organic and perovskite semiconductors are finding increasing application, both as photoelectrodes and as photocatalyst particles for making green hydrogen. You can see some examples here. I'm just going to give a little more detail on some of those areas. So this is the idea that you can have either an organic or a perovskite solar cell embedded in a photoelectrode, in this case, either to oxidize water to oxygen, or here actually reducing protons and CO2 to CO and hydrogen. Or we can have particles, polymers in this case, suspended in water, which when you shine light on them are making hydrogen from water. This is a significant challenge. So this is some of the first work we did in this area, where we were simply embedding a widely used organic bulk heterojunction solar cell, but simply replacing the top contact, which would normally be silver, with some sort of a catalyst, in this case, for proton reduction. And of course, the challenge here is that putting a solar cell in water to drive the chemistry is a very different environment to how a solar cell normally works. And so we understood that in order to get these to work, we need to both replace the P dot very often used as a hole collector with something which is much less water sensitive. And also we needed to use, in this case, an ALD titania layer to try to protect the active layer from water. And we started to get some reasonable performance. Of course, this is still on the seconds time scale rather than the hours time scale or days time scale, which you need, and indeed years time scale for solar cells. Maybe more wacky example is where Taco Lee and my group recently showed that he could use a lift-off process in water, where essentially you create a film of polymer on the surface of water and you lift up your bulk heterojunction through the water to deposit your organic layer on the surface. It's a rather elegant way to create or to deposit organic layers without disrupting any layer underneath. And in this way, we were able to take the same PM6Y6 materials, which are yielding those very high performance solar cells, and make photoanodes for water oxidation, where this PM6 layer on the top was both improving the stability, but also suppressing recombination losses, because of course you have to accumulate lots of charge in this catalyst in order to drive the water oxidation. That charge in a catalyst can recombine with electrons in the active layer. The PM6 layer was very effective at blocking that recombination. That's interesting, but maybe what's more exciting is what's happening when we just take a very simple particle suspension. And so in this case, we took the same materials, PM6, are blended with either Y6 or indeed PCBM, and Jan Kosko from Ian McCulloch's group made particles of these by a simple emulsion technique using a surfactant to create nanoparticles like these, which is suspend in water. And when you deposit some platinum catalyst, that's these dots you can see on the surface, then you can start to drive proton reduction to water. Now, the efficiencies here are not the same as the efficiencies of solar cells. These quantum efficiencies are in the range of a few to up to 10%, not in the range of 80 to 90% we have in the solar cells. But these sorts of particle suspensions in water have a particular interest for low-cost hydrogen generation. Most of the cost analyses of how we could really imagine making cheap hydrogen involves some sort of suspension in water and shining light on it to generate hydrogen and oxygen or another oxidant. In this case, we're not oxidizing water, we're oxidizing ascorbic acid. In terms of kinetics, then of course we can do all the usual things and measure that the excitons are separating because of a junction with either the Y6 or the PCBM, and so the exon decay gets faster. And we can measure, of course, that the photoluminescence gets quenched because we have bad exon separation. But what's maybe more striking and interesting is when we looked at the charge generation and how long the charge is lived in these nanoparticles. And in this case, what we observe is that the particles are living for milliseconds to seconds. So this is an optical signal from one of these, actually the PM6 PCBM blend is the most striking, where we see quite a large optical signal simply from that particle suspension in water. We see nothing for the equivalent film. And what's going on here, we believe, is that by depositing these organic semiconductors in water, we change the ionic environment. We're making the system more polar, we're increasing the dielectric constant, we're making it more like a perovskite, if you like. And that results in the charge recombination being dramatically slowed, going down from nanoseconds and microseconds to milliseconds and seconds. We don't fully understand this, but it's certainly quite exciting because it opens up lots of opportunity to thinking about these sorts of bulk heterojunctions for driving catalysis in water. So to summarize, I hope I've given you some thoughts about what's interesting in terms of technology, in terms of both organic and perovskite solar cells, and also some thoughts about what might be exciting in terms of making hydrogen from sunlight as well as electricity. I've hoped I've given you some thoughts about how these solar cells work and how one technology can learn from the other. I haven't gone into all the details. You can see some examples of grain boundaries and all this sort of thing, which are exciting details when anyone wants actually to make an efficient device. But I've hoped I've shown you that there are some differences. How charges are generated are quite different between organic and perovskite solar cells. And there are some similarities. How we generate open circuit voltage is essentially the same in both devices. And indeed, how we analyze it is essentially the same. I, of course, must thank everyone who's helped the work I talked about today. Of course, most importantly, my own group, and this is my group as it currently stands, but of course, the work I talked about included the work from many previous group members, all our colleagues and funders who've been fantastic at helping drive this and enable this work, and my colleagues both in the CPA at Imperial in specific in Swansea, and collaborators from around the world. And with that, I must stop and thank you for your attention. I hope you found that interesting.
Yeah, thank you very much, Professor James, for enlightening all of us related to this. I'll not say not so new area, but yes, it has got a very far-reaching applications and towards the green initiative, and also resolving and solving our problems related to the energy requirements, especially in the developing countries like us. Well, there are a few questions in the chat section. Would you like to look at them, or shall I read out? Yeah,
I can see some. I can start off reading them and see how we get on. So I can see the first question is from Amit Kumar about the difference between inverted and conventional perovskite solar cells. So the directionality of charge extraction from a solar cell depends upon the contacts and the electrodes, on which side is the anode and which side is the cathode. And there's various conventions. And unfortunately, the convention of a nomenclature for inverted and conventional are opposite for perovskite and organic solar cells. For an organic solar cell, the transparent contact, which is normally the one at the bottom where it's deposited on the ITO, if that's the whole transport layer, the whole collection layer, then that's a conventional organic solar cell. And if the bottom contact, the ITO, is the electron collection layer, then that's an inverted solar cell. And it's the opposite for perovskites, which is just unfortunate. Is how they were developed. So for perovskite solar cells, the conventional ones have the electron collection layer on the bottom, on the light absorbing side. I hope that answers the question. You can add more questions if you wish. And then in the organic solar cells, where a donor acceptor model is utilized for designing a solar cell, we generally use bridging molecule for donor acceptor sites. What is the effect of bridging on designing the donor and acceptor model for organic solar cells? How would it affect the charge transport if we designed a molecule without bridging molecule? So there's two different, I'm not quite sure what the question's about here. It's certainly a very interesting question. In the organic solar cells which I described, there wasn't explicitly a bridge between the donor and the acceptor. They were simply blends where the donor and the acceptor assemble. There is interest in having ternary blends where we have one material which acts as a bridge between the primary donor and the primary acceptor. Those are starting to gain interest. And of course, sometimes the alkyl side chains, which can help make the material soluble, can act as a barrier between the donor and acceptor as a bridge. Yet we can also have organic molecules which are donor bridge acceptor. It's a single molecule where the bridge is used to connect elements of that molecule which are more donating and are more accepting, and certainly there the bridge is more important. I'm not sure if that answers the question. You're welcome to ask more questions if you're with that. And then Anit asks where these tail states exist and how to decide whether it's a tail state or a shallow state. So this is a bit of a mystery. And of course, it's a key question. First of all, by tail state, I mean states which are relatively close to the band edges. These are often also called shallow trap states. And so for me, the difference in there is, I can use the word shallow trap state and tail state interchangeably. In many materials, and not just in perovskites and organics, tail states show exponential distributions. And so very often we observe that the density of tail states goes down exponentially as you move into the band gap. The physical origin of these tail or shallow trap states is often rather uncertain. Very obviously chemical defects, differences in conformation of a material, ion vacancies in a perovskite, grain boundaries in a perovskite. These all have a potential to form tail states. In some cases in perovskites, they also form deep states. But it's not necessarily the case. Another example of tail state, which is maybe a little more surprising to think about, is when you increase the crystallinity of an organic material, you lower its band gap, which means that if you have a rather amorphous organic film, when you have patches of crystalline material, these will function as regions of lower band gap and therefore appear as tail states or shallow trap states in a blend. You wouldn't normally think the crystalline areas are traps, but functionally they will behave as such. The important point is that this shallow trapping or charge relaxation into tail states is reversible, which means that the carriers can undergo a continuous process of trapping and detrapping. And indeed, in both the perovskite and the organic solar cells, maybe it's clearest in the organics, then most of the evidence suggests that most of the charges which end up getting extracted get extracted via trapping and detrapping from these tail states. I hope I'm answering the question sensibly. Then I've got a question from Tungabid about, please tell us a little bit more about the different polymers you've used, and among them, which is more efficient, and among PDOT and simpler polythiophenene, which is better. So if I focus on the light absorbing materials, then in the organic solar cells, then of course it's a donor acceptor pair which makes a solar cell, and so we can't design the donor without considering what acceptor we're going to use. There is no wonder class. I don't have any particular insights into what are the best donor materials. Clearly, things like PM6 and its analogues are working very well as organic solar cell, as donors in organic solar cells, and now there's also interest in polymer acceptors. One of the things I'm aware is that in order to select a polymer, you don't just have to think about the efficiency, but also the stability and the cost. And these also vary, but I could spend a whole talk just on that. And if you think about the technology and what you want to scale up, then very often the highest performance materials are not the one which is the most stable or the most scalable. The perovskite, where does it come from? So for these methyl lead iodide perovskites most easily, these are fabricated from making a solution of methyl ammonium iodide and lead iodide. And that solution is then spin coated, the solvent dries, and with modest thermal heating, then you form the perovskite. It's quite remarkable. If you watch it happen, you can just you deposit it as a yellow film, and a small amount of heating, and it turns black. can we utilize a CELAR method for deposition of perovskite film to solar cells? I'm sorry, I've forgotten what the CELAR method is, so I can't answer that one. Maybe if you can answer a bit later. Oh, yes. I mean, DSCs, the model uses a donor bridge acceptor model. Yes, that's certainly true. And that is one way to help separate the charge. The beauty of dye-sensitized solar cells is that we can orientate the dye molecules on the surface. And so we know which direction the dyes are pointing compared to the titanium substrate. In the organic solar cells, it's much, much harder to orientate one molecule relative to the interface. And that makes this idea of a donor bridge acceptor molecule, which was very good at separating the charges in dye cells, much harder to apply to the organic solar cells. I hope that helps at that point. I kindly provide images of this. I don't know if I can do that now. Yep, and bridging is mainly done by pi conjugate materials. Yes, absolutely, that's all true. And in dye cells, that's very important, but it's harder to apply to the organics. In perovskite structures, the stability is an issue. So people are working on whole transport layers to improve stability. So stability is a key for both of these technologies. And there are many different aspects to stability, and it can be the thermal stability of the active layer, the impact of light and oxygen, and certainly the transport layers are one of the key factors for stability, either because they help to encapsulate the active layer or because sometimes you have chemistry between the active layer and the transport layers. I'm not an expert on what are the best transport layers in a perovskite to enhance performance, but I know that's a big issue. I'm sorry I can't be more precise on that for now. I think that's the questions answered.
Thank you, Professor James. You have taken up, all possible questions, and I must appreciate your kind gesture for taking up all the questions. And for all the attendees, it's late evening in India. It's around 8:30 p.m.
Yeah, I'm sorry.
Yes. No, but I can still see so many people, and they are all science enthusiasts who have been there with us. So on behalf of the National Academy of Sciences, India Delhi chapter, and the host institution, Deen Upadhyaya College, I would like to thank the speaker, that's Professor James Durrant, as well as all these attendees who have been there with us for listening to his webinar and asking all possible interesting questions. Thank you very much, Professor James. And thank you.
That's a pleasure. Thank you for your time.
Sure. Thank you. Thank you very much, sir. Okay.
Bye-bye. Thank you.